All right, do it. Good Lord. They're being stupid if you're listening to these notes. They're trying to get on my nerves. All right. Are you guys ready? Um, yeah, you're in the big red note packet. If you don't have one, there's some more over on the file cabinet over there. So my goal today by the end of the hour is for you to be able to do this worksheet. You'll notice if you read the directions, you don't need to come and grab it, but if you're not here, there's one in Schoology, I think, in the files. But you'll have 10 what are called parametrically defined equations, and you're going to be graphing them by hand, and then you also have to eliminate the parameter. So we're going to do three things today. We're going to make sure you understand what they are first, and then we're going to graph by hand, graph by calculator, and then do what's called eliminating the parameter. So it's about 3 days of a pre-calc lesson in about a half an hour here. So we're going to cruise, but it's easy. So you'll be fine. All right, so a parametric equation allows you to add two things, or even sometimes more to a graph, but one of the primary things that it allows you to do is add direction or orientation, some books will call it, but a direction for sure. You can tell a parametric graph which way you want it to go, where for equations in your function grapher, like your y equals, you have no control over which direction your calculator chooses to graph it. In parametric, you can have it start from the right of the screen if you want, or the left, or in the middle. You have total control over the direction, and you actually have control over the speed, which last hour turned out being kind of fun when they were messing with the speed, because you can control it with what's called a t-step. So although we were graphing a circle and we were just having to go about this fast, it actually started over here, but it went like this. We had to go nice and slow. Some of them changed their t-step to pi fourths, and they actually ended up making like a perfect octagon instead of a circle, because it controlled how fast it was moving, and so it makes kind of cool stuff. To do this, what you do is you add a third variable. It's usually t, sometimes it's a theta, but it's usually t, and usually t for the word problems tomorrow will stand for time. So what they look like is when we go to parametric mode in your calculator, it'll no longer say y equals. It'll say x sub 1 of t equals and y sub 1 of t equals, and then x sub 2, instead of y1, y2, y3, y4, it'll be x sub 1 t, y sub 1 t, and then x sub 2. So you can do multiple parametrics. So they end up being entered as some function of t. It might say x equals t squared minus 4t. And then y is also some function of a third parameter. And that third variable, and again, this is just some vocabulary at the beginning here, that third variable is called the parameter. So it is the independent variable that now controls two dependent. When you graph y equals, and it's a function of x, y is actually dependent on x, and x is independent. Both of these are dependent on t. Does that make sense? So it's a third one that controls both of them. So it's called the parameter. And the graph itself, like when you look at it, is either called a parametric curve, or some books will call it a plane or a planar curve. So again, how are they different from just your regular old function? They add stuff to the graph that functions don't have. And it actually allows you to graph things that aren't functions. So, and again, I told you they add speed and direction, so that's not really new. So I'm going to start super basic, just so you get the idea of what they're doing. If I were to ask, go ahead TJ, if I were to ask him to go to his function grapher and hit y equals and do x squared plus 1. Just go ahead and do it. I know you know what it's going to make, because you know. By the end of the hour, you're going to know what some of the parametric ones make. But we're going to pretend he didn't know, and he goes to his calculator, and he enters y equals x squared plus 1. He has no control over what his calculator does, right? It comes in from the left of the screen and swoop down, correct? He has no way to make that change. He also gets the whole parabola in his entire screen. For parametrics, you can control that. Like, you can decide whether you just want maybe the left lobe or the middle lobe, or if you want it to go backwards. They say it's used a lot in what's called kinematics, like things with motion. So that's where parametrics get used. Polar is a little more useful. So let's go and talk about how you used to do this when you were in like 5th grade and you didn't know it was a parabola. You guys have done it so much, you know. But if I were to put up any like parametric model, you wouldn't go, oh, I know what that's going to make, because you've never done it before. So the very first thing you learned before, and I know I'm insulting your intelligence, I'm doing it on purpose, because I want to show you it's exactly the same thing when you do parametric. You take and you start plotting these things. Your X choice determines your Y. When we do parametrics, we'll be adding a third column over here, and the T is going to be controlling both of them, but we'll still be plotting points. So when I plot points on here, what could I let X be? You could, and that's very logical. Why let it be? And so when you're graphing yours, last hour they got to number 5, and someone was choosing the same X value or T values that they chose for the other ones, and I said, you know, be nice to yourself. What you choose for T is what you have to do, and 5 has a root on it. So who would be really nice to choose for your T values? 1, 4, 9, so you, just like in 5th grade, you have control over your independent variable, which used to be X. So I could say I'm going to have it be 0, and I could go plot that one right now. I get to just randomly pick. For parametrics, you don't really randomly pick anything, but let's say I did -1, and then I'd have a 2, and then a 1, and a 2, and a 2, and a 4. And if Adam were to decide to plot them in any order, it doesn't matter. He could say, I'm going to do the 2, 4 next, just because, and then I'll put this one over here, and then I'll put the 2, it doesn't matter. So he just kind of randomly puts the dots on there, correct? And then what does he do with the dots? He just connects them, and it doesn't matter. Like maybe Nordstrom goes this way, and maybe Adam decides to go this way, and then maybe Sam's like one of those people who does the right half and then the left half. It doesn't matter. You're staring at the same thing. But for parametrics, you get that control over your graphing calculator. Like you get to control where you want it to start, where you want it to end, and what direction you want it to come in from. So we're going to go do what's called parameterize this situation, and then just so you can see it. So now I've got what's called a parametric system right here. My T is controlling the X and the Y. So you still make a table, and it's still just as easy. It just has 3 columns. So your tables, when you do your homework, are going to have 3 columns. Again, I have to cover this even though it's not difficult, because you need to have a concept of the graphs. So my T choice has been told to me. On your worksheet, on a couple of them, I told you. Where's one? I told you on number 2 what to use, right? If it doesn't say, it's just like as if you were doing it back in the 5th or 6th grade. Pick things to be nice to yourself, and pick things that are legal. Like you can't root negatives, so the ones with roots, don't choose negatives. If you have to cut stuff in half, choose evens. Do the same thing you would have done back when you first learned how to graph. This specifies, though, it says to go from -1, 0, 1, 2. So I plug the T in, and it is going to control both of these. So when I plug it in here, I'll get -1, 0, 1, 2. X is the T. And then I'd square it and add 1. Square it and add 1, sorry, my pendant, right? Square it and add 1, square it and add 1. But for parametric functions, there's a little bit more to it. Unlike that last one where I decided just to plot the points however I felt like it and connect them however I felt like it, you have to start at your first T choice. I have to start at -1, 2. I usually put a bigger dot there than at the rest. It gets a name. It's called the initial point. So it needs an initial point, and then you plot them in order. 1, 2, and then let's just say 2, 5. It doesn't really matter. This last one's called the terminal point. Your calculator will travel from the initial point to the terminal point as fast as you want to make it go. So we'll talk about the calculator in about 5 minutes, but you can control how fast you want it to move. For your parametric graphs, you also need to put these arrows on that indicate direction. That's common. So parametric graphs, that doesn't look a whole lot different than its rectangular component on the first page, but I controlled where it started, I'm controlling the direction, and I'm controlling how much of the parabola I get. And my calculator, I can have that control. It won't just make the whole one that's sitting on TJ's screen. So anyway, Nothing exciting yet, but the word problems tomorrow are actually cool for this. Anyway, so, oh, Monday, yeah. Let's go take a look at this one and see what's going to happen. What I do when I change where the t is, you could probably anticipate, maybe I don't even need to redo this one, but just anticipate changing my t values. How will that change my graph? If you don't know, I'll go do it, but what's it just going to do, Ashley? It just moves me to another part of the parabola, yeah. So instead of having that part, I'd have this part. Does that make sense? Do I need to plot these? It's just going to give me another piece, and that's why I said I'm going fast through like 3 days of content, because you guys should get it. Now, I told you you also have control over the direction. Watch what changing this sign, so I'm back to that original one, and this one I'm going to do. I'm going to make my t choice still control the x and the y. And I'm still going to go from -1, 0, 1, 2. So my time is still going forward if t represented time, but I'm going to make my graph go backwards, which you don't have control over when you're in rectangular mode. So now it says x is the opposite of your t. So now it's going to go 0, 1, -1, -2. Do you see how that little sign change is now going to start me on the right and move me to the left? So messing with the range of the t just moves you to a different piece of the graph. Messing with the sign of the t makes you go backwards or forwards. So when I go plot this one, I will now start at 1, 2, and I'll be starting over here, and then 0, 1, and then -1, 2, and -2, 5. This is now my initial point at traveling to the terminal point. Does that make sense? You do not have that control when you're in function mode at all. And you might say, well, why do I want that control? Well, you want to control movement, right? So this is everything I already told you out of a pre-calc book. So we're just going to go do one here by hand, and then we're going to do its counterpart on the calculator. All right, so if I asked Adam, what does this make? Because it's not something he's used to seeing, he doesn't know. But if I were to ask you, what does this make? Do you know what that makes? That's a 2. What does this make if I were to graph it? Yeah, he knows exactly. Like you guys can't see what he's doing, but he made the motion for that thing. Only because you've seen it a bunch, correct? So I know what this one's going to make because I just did it last hour. And I know what the some that have curvature make. By the way, what happens if I do plus or minus? Then what do yep, then I get this. You know that. So let's go take a look at what this one makes. So your t is going to go from -2 to 3 because it said to. If I had my choice, I might have chose just evens, but this, when it specifies your t domain, you have to use that. So what do I do for the x's? I just square and subtract 4. So just super easy. Square and subtract 4, square and subtract 4, square and subtract 4, correct? Square and subtract 4, square and subtract 4, and square and subtract 4. Next step. For the y's, I just cut them in half. So a half of it, 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 a half of it. It is not a function, but I'm not in function mode. I've got 2 x's giving me 2 different y's. Do you see how I'm going to be able to graph a non-function? So when I go plot them, I have to start here. What did I say this guy's called? The initial point. So when we graph this on the graphing calculator, it will start right here. It doesn't do what the function mode does and starts at the left of the screen. It starts right there wherever the first t caused your first point to be, and then it'll be at -3, -1/2, -4, 0, -3, +1/2, 0, 1, and 5, 3 halves. So it's going to head like this and go like that. Starting here, when we go put it on the calculator, you'll see it do exactly that. It'll start down there on the y-axis, and it'll just head around and go forward and stop. If I did it in function mode, I'd have to enter it as 2 pieces. You'll see when we do what's called eliminate the parameter. My calculator would graph the top piece from left to right, then it'd graph the whole bottom piece because I don't have control over it. All right, so you gain a lot of movement control with parametric equations. So I'm not going to do this one because I don't need to. But what I want to do is have you take out your calculator, and I want you to First of all, you have to go to mode and switch to parametric. So go hit your mode. I'm not going to open mine because it makes my screen go super slow. So go to your mode, hit parametric. When you hit your Y equals button, now you're going to see a totally different view than you're used to seeing. It's going to say x sub 1t, y sub 1t. So, and we're only going to do one parametric set. So go ahead and enter those two in there, the t squared minus 4. Notice now when you hit that xt theta button, when you're in parametric mode, t is going to pop up as the independent variable. So go enter t squared minus 4, and then t divided by 2. Any questions? Yeah, it does matter which one's which. The x is the t squared minus 4. Just wait. Just wait. I'll get to the window in just a second, but go ahead and make sure you're in parametric mode. The X gets put in here, Y in here. These were our two from the previous page that we did by hand. Now, just like in function mode, you need to set the window, but the window looks a lot different. Your T has to go from what it said to. We were going from -2 to 3. The T step is not, this is where you have to be careful. You might say, well, we went by ones. We did. Right? But when we graphed it, we certainly didn't say, well, we're going to go here, and then here, and then here. We didn't jaggedly. We knew to sort of curve around. Your calculator doesn't know that. So what that's controlled by is the T-step. This guy is who's in control of speed and accuracy. So when you gain speed, you lose accuracy. So there's kind of a sweet spot for that. I actually think it's about 0.05 is my favorite T-step. It tends to go fast enough where I can see the movement. It doesn't, but I've never really had to switch out of that, to be honest. I'm going to have you mess with it in a second. But for now, call it 0.05. Go ahead and set -4 to 6 by ones. And for the y's, it looks like we can just go, I don't know, -3 to 3 by ones. It doesn't matter, just so we can see this. If you hit graph, you'll see that you forced your calculator to start here and move in this direction because it moves in the direction that are graphed. So your calculator doesn't put the arrows on, but that's what's happening. Now watch and mess with the T-step. All right, if you make the T-step 0.1, see if it speeds it up or slows it down. Now I'll tell you what your calculator's doing. Okay, it's sped up, correct? Now if you make it 1, super sped it up, right? Because what it's doing is it's actually going in linear steps, so it's going dunk, 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 not like tick, 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 tick. Do you see what I mean? Now, if you set it at 5, watch what it does. Set it at 5 and understand why it does that. Do you get it? Like, what, you have control over it. Why does it do that? It just gives you this line. You said, I know why. Why? Yeah, it's like on the table. It's just getting this dot and then going to that dot, and it's connecting them super fast. In the same, does that make sense? So when you do that T-step, it's not the step that you use when you make your table. Because you're the one who can, like, you're the one who knows it makes a parabola and makes it turn. You know you don't go like this when you make your parabola. But your calculator doesn't. All right, so we're going to really play with that T-step when we get to the circles and ellipses, because it's actually pretty interesting what you can do that to somebody not in this class, they would think you were graphing something very difficult, but in parametrics it becomes easy. So before we go do that though, that was two of the things I wanted to make sure you knew how to do. How do you graph by hand? Are we good with it? You just make a table. And then how do we graph on the calculator? Now we're going to do what's called eliminating the parameter. What that means is you get rid of it, that's what of t, and go, I guess I'm going to say go back, but go back to y as a function of x. Notice when you do that, though, you lose things. You gain like more clarity in what the graph's going to look like because this is what you've been taught for 12 years. is y's as functions of x. So when it becomes x squared plus 3x plus 5, you're like, oh, it's going to be a parabola that opens up, because that's what you've been taught. But you're going to lose control over what part of it you want, how fast you want it to move. So how do you eliminate a parameter? It's just algebra. This isn't calculus today. It's algebra 2 and pre-calc that we're going to need to do the calculus of it. So here's that same one we just did. And you wouldn't have known that it would have made that loop thing that we just did. But once we eliminate the parameter, this is in the second equation. It is for this one, but I'm going to have you write in the easier equation. So you don't always think it's the second one. So what you do when you eliminate the parameter, if it's algebraic, like these are polynomially and lines and stuff, you just take whatever one's easier and you solve for t. So you're going to say t equals 2y. Pick the easier one. So when you're doing your worksheet, you can pick either. But I'm just going to go, what kind of a t is that? It's a pretty one. It is a z. Sorry. I'm saying here, if I'm you're welcome. All right. So, oh. Oh. Yay. All right. So then what you do is you go put this in for t in the other one. So you're going to say x is equal to t squared minus 4. And then what you do so that you can gain clarity. So like in our regular, it's called the rectangular system, we gain clarity but lose everything else. All control of movement. What I mean by gain clarity is once you solve this for y, it usually becomes something that you already know. So when I solve this for y and I add 4, right, and I divide by 4, and I take a square root, what will I have to put in front of the square root? Plus or minus, which will make the 4 on the bottom a 2 because I was supposed to root it. But I'm just solving for y nice and easy. That's why I can go through 3 days of pre-calc in a half an hour. I'm just doing stuff fast that I wouldn't do if I couldn't. So now would you have known what this looks like? You'd go, yeah, it's going to do this on one side and this on the other, but you lost control over how much of it and how your calculator does it. So actually now I want you to notice what your calculator does. Hit your Y mode button and go back to function mode. You don't ever have to clear anything out of your other modes. They are in separate memory banks in your calculator. So the minute you go back to function mode and hit y equals, it'll have the last function stuff you did. When we do polar, we might be doing some really ugly stuff. It doesn't matter if we then move to parametric because it goes to a completely different memory bank. So you can have stuff loaded in all three and your calculator doesn't mind. So if you go back to function mode, it's going to have in there the last function you entered. Go enter our answer that lost the parameter, because that's what it's called. We eliminated the t. And so we have to enter it as two pieces. Understand why? Because it's no longer a function and I'm graphing it. So when I lose control, this is how now your calculator does it. I can no longer tell it to start here. I can no longer tell it to go in this specific direction. I can no longer tell it where to stop, and I can't tell it how fast to do so. I only have this option of now my calculator is going to go this left to right. That's how it graphs it. And then it's going to do that left to right. It looks like the same graph, but it's different movement. So just kind of get what the parameterization does to it. It totally gives you control over movement. And honestly, what you lose from rectangular, that clarity, if you just did these for like a couple weeks, which we're not going to do, it'd be as like if I asked Nordy, what's this going to make? And he'd say, oh, it's an upside down parabola that opens down from 0, 3, duh. You would get that good at the, we're going to throw one up in a little bit, and you guys are going to go, oh, it's an ellipse with the center here. You're just, it comes very quickly to kids at your level. So I don't think we need to do any more eliminating the parameter of just regular ones. It's just substitution. But here's what I want you to do. We're going to go do this one by hand, then on the calculator, and then we're going to start tweaking it, and I'm going to show you what happens. So by hand, this has a parameter. It's not t, it's theta. So theta is controlling x. You could call it x of theta. Theta is controlling y. So when I go on here, my obvious theta choices would be 0, and then I'd use my unit circle. I'd go by pi halves to pi to 3 pi halves, and then I'd go to 2 pi. Keep in mind though, watch, this is not the theta step or the t step on our calculator. That's what I'm choosing because I don't want to go by 0.01. It'd take me forever, right? So I know what I'm going to do with my pen, but my calculator doesn't. So when I go plug in a pi halves here, or I'm sorry, a 0, I'll get a 3 cosine 0, which is 1, and then a 0, right? Can I go fast through that? This is why I can do so many days of pre-calc in one day. We should be able to zip through the table. What's the next one going to be? 0. And what's the next one going to be? -3, 0. What's the next one going to be? There we go. And I'll end the same place I started. Now watch when I graph this parametric equation. I have no control over where it starts. I mean, I have total control. That's what I meant to say. I'm going to start at 3, 0. So when we do this in our parametric function option, we will be starting at 3, 0. It's going to pull it up. Now I know to curve, but my calculator doesn't know not to connect them with a straight line. Does that make sense? So that's why my T step when I go do this in parametric mode is not my step that I do on my table. All right, you could predict it's going to make a circle. Now watch this. If somebody were to ever say, can you graph a rhombus on your calculator? Most people would go into function mode and start doing some piecewise functions and piecing lines together, or an octagon. But you guys would go, oh, just do a circle and do a T-step of what? Of what? To make it go from here to here. Pi halves. Go try it. So go on, mess with your T-step for this, and you'll see some polygons that you can create that most people who don't get this far in math think they need to be created with a bunch of complicated piecewise functions. Yes? The unit circle is actually the first parameterized function you've ever seen. Yes, because it's cosine theta sine theta. Now, if you set it to be pi fourths, you're going to get like a, what do you get? A hexagon, right? So let's go into your calculator. Go from 0 to 2 pi. Have your t-step be like 0.05 so you can see it make the circle. But then and again, x min and x max can just be -3 to 3 by 1s. We're not going to exceed the 3s. Do you know how to get your window to square it up too? Because your calculators are made longer than they are high, so your circles end up looking like this. If you hit zoom square, it'll square it up. So what number is zoom square? Zoom 5, thank you. We'll make it, so if you wanted to make a regular hexagon on your calculator really fast, you can do it in parametric mode. Go play with your T-step a little bit. What if I wanted a bigger, oops, all my papers fell on the floor. If you're listening to this, I'm just letting them play on their calculators and mess with the T-step. One thing too, if your T-step makes it go too slow, like if you try 0.01, go ahead and try it, and it's just creeping along, you don't have to wait for it to finish, because that's going to happen to you tomorrow. We're going to be launching things, and your calculator is actually going to be graphing their path. And if your T-step is too slow, Melissa's going to be sitting there going, oh, come on, this rocket is never going to land. Just hit on, and it'll stop it. So if your T-step is too slow, it's going to be going like this. Do you ever get like that? And you're like, ah. Why did they never teach us that we could stop the graph? If ever you're sitting there and the graph is taking forever to make, hit the on button and it'll stop it. Yep. All right. Are we good with that? I'll have to look. All right, we'll go back to the calculators in just a second. What I want you to do, though, is I'm going to show you how to eliminate the parameter the easiest way for trig. So back to your notes. We're not quite done. I want you to write this. For trig, I told you for those algebra-based ones, just solve for t in terms of one of the other variables and substitute. Just use some algebra 1. For the trig ones, like this was, it was 3 cosine, 3 sine. You don't really want to solve it for theta or solve it for t because you would have to do arc cosine and arc sine, and we all know we hate those, right? So the easiest thing for the trig ones, and I know I put a little star by this because it's me telling you I'm probably going to test you on and eliminate the parameter of a trig one because that algebra one was like algebra 1. So for the trig ones, you're going to use your Pythagorean. It's easy to do. It's just some kids leave this one blank when I test them because they don't remember that they shouldn't be doing it the complicated way. It should be very easy for you to eliminate the parameter for the trig ones. Use your trig Pythagorean identities. All right? The main one is that cosine squared plus sine squared equals what? 1, and you get all the other ones for free. So there's one on your worksheet. You'll notice the bottom one. Is it a secant tangent or what is it? Yeah, so you're going to write this so it has secant squareds and tangent squareds in it. You're going to make the use. Now watch how it works. What you're going to do is go back to the original. You know how it was, what was it? X equals 3 cosine theta. Wasn't that the original? Right, so if I solve it for just cosine, not for theta, just leave it as x thirds equals cosine. And the other one was y equaled 3 sine theta. Just leave it as y thirds equals sine theta. Then if you don't solve it for the t or the theta like we did on the algebra ones, it makes it messy, and I don't even know that you could stumble upon the correct form. Go plug these in over here, and you'll get x squared over 3 squared plus y squared over 3 squared equals 1. And then what do you think I'll multiply everything through by? 9, and you get that algebra 2 formula. They said, well, this is the standard form for the equation of a circle centered at the what? Origin with radius 3. And most kids actually with this, when you first teach it to them, sometimes like if that's equal to 4, they'll tell me the radius is 4 because they don't get why that's squared over there. And you'll see with the parametric, you get actually more clarity once you understand them. Watch this. What would happen if I just changed one of these two to a 5? You should start to get it. It's going to make an ellipse. Go try it. It's on your calculator. Go pick one of them, and it'll change the major and minor axes of your ellipse. So if you go just change this one to a 5, it's going to make an ellipse. Will it be a longer or taller ellipse? It's going to be... I'd change the cosine one. So mine's going to be going out to 5, up to 3, so it'll make like an oval this way. If I change the other one, it would make an oval this way. It switches. Don't they call them major and minor axes in pre-calc? Well, that's what just changing this number in front just immediately changes a major minor axis. So it's kind of cool. On the next page, could you write... For example, I told you there's parent functions for these, just like when I asked Nordstrom, what's this going to make? And he said an upside down parabola. I should be able to ask you guys maybe right now, no matter what this A is, based on what we just did, what's it going to make when I graph it in parametrics? Circle, centered where? Now you should also be able to figure out how I can move it off the origin. Well, I could just add. Yeah, if I added a 2 to this and a 3 to this, I'll just move my center on over. So it's intuitive, because when you do it in algebra 2, they'll say, well, this has a center at 4, and you're like, well, why isn't it negative 4? Where this one, if I add 4, it's pretty clear the center is going to be at 4. Do you see what I mean? It's not the opposite of what you would think it is. It's exactly what it should be. You know how they always say it's the opposite of what you think it would be. And weren't you ever going, well, okay, I'll memorize that. But why is it? It's because if you remove the parameter from this, watch what happens. So what would my radius be? A. Watch me write a proof. They're easy to write. I'm going to take this 4 off of here. I'm going to solve it for cosine t and say x over a, your cosine t. I'm not going to solve it for t itself, just for cosine. Similarly, I'll say y over a, guess what? Your sine t, right? You guys are really listening. This is going to be easy for you. Then I told you for the trig ones, use your Pythagorean identities. Cosine squared plus sine squared equals what? 1. So here I get my x squared plus my y squared equals what? A squared, and I get that it's a squared because it's so much clearer in its radius is a, not a squared. Does that make sense? So it's actually kind of cool. So on the next page, Now watch what happens. You probably can anticipate. Like, you guys are super listening. I'm probably on day 3 or 4 of pre-calc right now, but we're doing a whole chapter of parametric pre-calc in 2 days. But we got it, right? So what do you think is going to happen when I add this and add this? Its center is going to change. Yeah, it's still going to have the same radius, but it's going to move over to h comma k, not the opposite of h comma k, like not the opposite of what I think it should be, but exactly what I think it should be. Furthermore, if I wanted to make it an ellipse, you should know what I should do. Yeah, change one of these. If I want it to be stretched along the x-axis, make this number bigger than this one. It's so clear. Like I said, you lose clarity. You only lose clarity because you're not used to this. You actually gain way more knowledge about the graph. So let's go prove that. Watch this one work out. I would say x minus h, because I'll subtract that, over a is what cosine is. You guys agree, correct? Then I go and say, well, that's why it's the y minus in the formula. I don't know if you get what I'm talking about. Like the algebra 2 formula, they just give it to you and say, this is the circle. Well, the reason there's an x minus h squared and a y minus, the opposite of what you would think, is from eliminating the parameter. All right, and you'd get this over a equals sine. What do these two have to do? Add up to 1 when I do what with them? Square them. So watch, I get that x minus a squared over a squared plus, am I writing too fast? I feel like I'm writing really fast. You're keeping up? All right, because I want to give you a lot of time to work if I can. All right, and what does this have to equal? 1. So what am I going to multiply through by? And that's where the one from algebra 2 actually comes from eliminating the parameter of something that's actually controlled by the angle that you're turning when you go around the circle. Isn't that what? Do you get what I mean? A circle is really not what your calculator does, where it does this and then it does this. This is a circle, and this is that. So I think you kind of get it, which is cool. All right, next page. I'm almost done. Nope, not there. Isn't there one on the bottom here? That's the one I want to do. Okay, so let's take away the graphing by hand, and I told you by the end of the hour, you should maybe be able to predict, just like when I said what's y equals 2x plus 1. It's a line. What is this? This is an ellipse. All right, let's write that. It's an ellipse, just from having done it for 25 minutes. You guys you got it down, actually. It's an ellipse. Tell me about the ellipse. There we go. Centered at exactly where it looks like it is, not the opposite of what I think it's going to be, right? What else do you know about the ellipse? Major axis of x. You can even tell me its length. You don't need a formula like they give you when you do. You can, because it's intuitive. So, like Ashley, you're gaining clarity, not losing it, even though it looks not what you're used to. So this would have major x axis, and you actually just told me how long it is. How long? 6. In algebra 2, when you have it in its standard rectangular form, you have to kind of think, that's a lot harder to think out. You know what I mean? Because you're working with an r squared, and then you have to think, well, that's r is this, but I need to double it because I'm going this way and that way. And so this is way clearer. And a minor y-axis, right? And on my minor axis, how long will it be? All right, so I actually have a very clear idea what my calculator is going to graph. So let's do it by hand, and then we'll go to your calculator. My calculator will not plot 1, -1. My calculator will start. Let's kind of think of where. If I made a table, oh, this should be 2 pi, by the way. It's only going to make the top half of the ellipse. That's my fault in the notes. If I go put a 2 pi over here, let's think about where the calculator will start the ellipse when we go to parametric mode. It wouldn't be fun to try to do this in rectangular mode, but where's it going to start? 4, what? Yeah, you'll notice 1, 2, 3 to the, I could have figured that out without even plugging it in, because I've gained so much clarity. I know it's 6 long, so I just go 3 this way, right? It's going to be graphed like this when you do it on your calculator. And it's going to go in this direction, and it won't piece together any top or bottom halves. So go to your calculator and go to your parametric mode. Do 3 plus cosine t, -1 plus 2 sine t. Go to the window next. What should you set this to go by? From 0 to 2 pi by what? It's a good question. What should your t-step be? Because that's actually the most important part. I would do 0.05 or 0.01. Oh, it says to use 0.1. That's going to go fairly fast, but you shouldn't lose clarity on it. Again, some kids will set it to go like if they made a table, you would choose pi halves. Remember, if you do that, your calculator is going to go and do some linear connections every 90 degrees. What do you think? Did you get it to graph the ellipse, and does it look like it should? I just want to make sure I'm not working my calculator because it's been really messing up my smartboard. So go set your window again for your so then you could make like what's called an oblique hexagon. It'll be like this if you did a t-step of pi fourths, I think would do it. Try it. Do a t-step of pi fourths.
What's the major and minor axis?
Oh, the longer one is called the major axis, and it'll go with the bigger number. So because my bigger number was with cosine, and cosine's controlling x, it's going to be elongated. Now, this is a good question, because that's not how it gets taught in Algebra 2, because it's not. Next up, once you're done on your calculator, to wrap up the day, I want you to go eliminate the parameter on that ellipse. And you should get the form it would have been in conic sections in pre-calc or algebra 2. But you lose actually now because, again, the first 10 minutes I said you're going to lose clarity. You're going to gain it with parameters. Yep. I'll have to come and look at it in a little bit. I'm hoping you're in radian mode while you're in parametric mode. That's the first thing I check. Then I'll come look at it in a little bit. I know physics does that. This is kind of the level I test you at for eliminating the parameter. I ask you to do one of them on your test. It's not a big deal, but did you eliminate it there, Sparky? Or, I'm going to talk about that in just a second. No. So who eliminated the parameter? What did you get, Ashley? Yep. Okay. Over 4, right? And equaled 1. This is the standard form for the equation of ellipse that you get in Algebra 2. They put an a squared and a b squared on the bottom. And they'll tell you the bigger number gives you the major axis, right? So you have to think, well, this is actually a squared. So I actually have an a of 3. So I have to go 3 to the right and 3 to the left. You have to think that through. And that's going to be 6 long major axis, where it's a little easier when it was parameterized. A lot easier, because you didn't have to think, what's the center here? Is it 1, -1 or -1, 1? Well, they tell you it's the opposite of what you think it would be, right? So what do you say? 1, -1, but in the parameter one, it was very clear that it was a +1 on one and a -1 on the other. So I'm going to tell you a little bit about what the word problems do, because they're really cool. When you are taught motion first, I think it's like in Algebra 1, they'd call this T and this H, and they'd say, this is a ball or a rocket or something being tossed up, and then it lands. And then what would they tell you to find? They'd usually say the vertex or how long will it take to land, and kids are under the false impression that this is actually the path of the ball. It's actually not. It's actually charting the height of the ball over time if it were thrown straight up in the air. That's actually what this is. It only gives you the height of the ball. It's the height is a function of t. Wouldn't you agree? It gets higher and higher and higher, and then it falls. That's what this isn't the path of the ball. To actually graph the path of the ball, you have to use parametric equations, because there's lots of stuff that control it. That's not just time, like baseball. If I'm going to hit a ball, what might control how high it gets besides time? The angle. So there's going to be an angle parameter for sure. And also, yeah, that actually has to get added in with some physics. But yeah, the angle, gravity affects it because it's pulling the ball down. Initial velocity affects it. There's so much, how hard did you swing the bat, first of all? There's so many things that control its actual path. The only thing, though, that if you just throw it straight up, the only thing that's controlling it is initial velocity and T. But the angles doesn't matter. And you're going to see why with the calculus of it. All right, so for your worksheet, your job is you've got 10 parametric equations by hand. If you want to do it, they wanted graph paper last hour, so I went and got some. You're going to graph them, but then it also says to eliminate the parameter. The only one I gave you a time or a T window on is number 2. It means for the other ones you pick. What do you think would be wise to pick, like when you were in elementary school? -2, -1, 0, 1, 2, unless they are not applicable. Like on number 5, I can't pick those because I can't root negatives. On number 7, 0 is not a good choice because I can't divide by 0. But pick things that make it nice. The key's posted, but what I did, I loaded it last hour so they didn't have to open because it's a new topic, they didn't have to open their Chromebooks. I'll just kind of scroll. I'll have number 1 up for about 2 minutes and then number 2 up, and then you can look up here and see them. So let's see, I should have it. I'll show you how my work looks because you haven't, to be honest, you won't be graphing these by hand. You're going to be doing calculus with it, but it helps if I'm in Calc 1. Yeah, 2 I made you go a specific T, but the other one, I'll show you what my key looks like. I'll come look at it, Sam. Oh, I'm still recording.